All right, everyone, we are back in HED 241, Biostatistics and Public Health. We are on Part D, which is Inferential Statistics, Section 18, Sample Size. So sampling errors, an unbiased random sample, even that still has some sampling errors. So sampling errors can be evaluated with inferential statistics, but inferential statistics cannot be used to evaluate the role of the bias, which is why it's important to eliminate bias in the first place by using random sampling. So you might be able to tell whether there is random sampling errors, but you cannot tell how it's impacting the results. Okay, here's the general rule. The larger the random sample, the smaller the sampling errors. The larger the random sample, the more precise the results. Okay, precision. Precision is the extent to which the same results will be obtained if any random sample were drawn from the same population. Make sure you know that definition for your exam, please. An example, in a population of 10,000, two 500-person random samples would be more precise than two 25-person random samples. Okay. Makes more sense, right? Makes sense. The more people who you sample, the more likely it is to be more precise. Diminishing returns. If you've taken economics, diminishing returns is going to make a ton of sense to you. If you have not, which is obviously not required for our major, just know what's in here based on the textbook. And if you took economics or anything else, don't think about that. Simply think about what's in your textbook. So I want you to know increasing sample size produces diminishing returns on precision. Okay, it's like an example of that. Researcher A plans to sample 10 individuals at random from a large population. Researcher A plans to sample 10 individuals at random from a large population, but at the last minute, the researcher decides to increase the precision by increasing the sample size to 10 by selecting sample size to 20 by selecting 10 additional individuals for the sample. This is an increase of 100%. Okay, he had 10, and then the researcher added 10 more. Okay, so now you're at 20. It's an increase of 100%. Example 2. Researcher B plans to sample 1,000 individuals at random from a large population. Okay. Researcher B plans to sample 1,000 individuals. At the last minute, the researcher decides to add just 10 more people to the sample. So researcher B added the exact same number of people to the sample as researcher A, but only increases the sample size by 1%. Because 1,000 increase to 1,010 is only 1% increase, which leads to little effect on the results. Thus, this is diminishing returns on precision. Okay. National opinion. In national opinion polls, so this can be like voting, it can be whenever they do how people feel about the current president, and they're always looking at their opinions, and if they think they're doing a good job or bad job, or if they're looking at opinions on anything, really. That's what we're talking about with national opinion polls. It's ones that are done nationally. It doesn't limit just to like one county or one state or anything like that. So in national opinion polls, samples of 1,500 are usually adequate. Okay, adding more people is basically diminishing returns. Okay, so think about that. Going from 1,000 to 1,010 doesn't really do a lot of good. Same with national opinion polls. Going from 1,500 to 1,600 doesn't make a huge difference. Plus, what would be a downside of adding more persons to a sample? So I want y'all to think about that. What are some of the downsides to adding more persons to a sample? Honestly, one of the biggest downfalls is when having to do the analysis. It takes a lot of time to do data analysis. And if you have, instead of 1,500 and you have 3,000, and you would have gotten the exact same results with 1,500 versus 3,000, that's going to save you a lot of time as a researcher. You're more likely to find errors when there's more, different things like that. Okay. Well, let's look at differences among groups. So the smaller the anticipated difference in the population, the larger the sample size should be. So if you don't expect there to be much difference in the population, you really need to make sure you have a large sample. So an example would be researchers have developed a new drug for headaches. In the prescription, researchers say that the new drug will be only slightly more effective than the old. So you're saying there's an old drug, there's a new drug, and pharmacies and whoever drug manufacturers say there's not going to be that much of a difference. Okay? So with very small samples, so one group taking the old drug and one group taking the new drug, researchers may not be able to detect the small difference because the results would be imprecise due to the limited sample size. Because if it's a really small, you might not be able to see that difference because it's so small. If you only had 10 people, 20 people, you probably aren't going to be able to see it. You need a very large sample. Okay. So even small samples can identify a very large difference. So know that they can still. So all the people in these two groups, you have the experimental group and the control group. You have 100 people. Okay. Recently had a virus. So the experimental group, this group, is getting a new antiviral treatment. The control group is getting the old treatment. Suppose that some people died in each group. Okay, so you know in each group some people are going to die. Out of the 100 in the experimental group, only 5% died. But of those taking the old treatment, or the control group, 45% died. Okay, that's a big difference. How many of you would decide to take the experimental drug? How many of y'all would take this drug if you became sick with a virus? Probably most of you, okay? Only 5% died. 45%. If you decide to take the treatment, then you are acknowledging the importance of a large difference in relatively small samples, okay? If an anthropologist discovers a lost group of identical twins, 1,000 of them, really there's not going to be much variation if they were raised as identical. So if they were actually raised in the same home, not adopted or anything like that, then studying one or studying a sample of 1 out of 1,000, you should yield precise results. So populations with very limited variability, even small samples, can yield precise results. Okay, of course, the more varied the population, the larger the sample size should be. So if you wanted to look at the math scores of high school seniors in a large school district, you drew a random sample of 30. Okay, since there is likely to be more variation in math ability in a large school district, sample of 30, 40, 50, even 60, since it is random, might have misleading results. Okay, you might obtain many high achievers or honor students. So using a much larger sample will give you better results. Okay, because you expect there to be, usually in a school district, there's a pretty big difference between a lot of the test scores. So you want to make sure you capture everybody on the entire spectrum. Whenever you study a rare phenomenon, you should obtain a large sample. Okay, doesn't matter what it is. If it's just considered a rare phenomenon, make sure you have a large sample. Okay, here's an example. So in a 100-person sample, you might not find any students with HIV. Okay, so you might conclude that no college students have HIV. But what if you say STDs? Okay, so what you don't realize is that there's just over 12,000 new HIV infections in persons ages 13 to 24 per year. So that's still a lot. But just because you sample 100 people might not. That being said, maybe you did it in Jackson. Jackson has one of the highest HIV rates in the country. Okay, so you might go there and actually see it being so high, you're gonna think it's even higher. So if you only sampled 100 people from that one area, that would not be an accurate representation of the country. So, if you studied STDs, there's 10 million new STI cases between usually the ages 15 to 24. So if you studied that, you're more likely to catch some of those students in your population. So using a large sample does not correct for bias. So ask a group of people about a topic and you will always still get a variety of answers. Okay, so just because you have a really large sample, it doesn't necessarily correct all the bias at all. Okay, it reduces sampling errors, but does not correct for bias. Question 18, questions from section 18. Make sure you can answer all of these, and please let me know if you have any questions.